Potential vorticity is a variable that combines the absolute vorticity in some measure of the thickness of a column. If you think about the definition of thickness, then thickness was a measure of something thermodynamic because it was related to temperature. Hence, what we're doing is linking dynamic and thermodynamic properties with potential vorticity. We're only going to introduce a simple form of potential vorticity here, and the most general form that we usually talk about in meteorology is called Ertel's potential vorticity, after the scientist Ertel, who did the derivation of the conservation properties of it. In a generalized definition, potential vorticity is conserved in adiabatic motion. We're going to return now to the vorticity equation. We will remember that dF dt, where this is the material derivative of F, the planetary vorticity, is equal to V dF dy. Hence, we are keeping the variability of F with latitude explicitly in the equations. And dF dy, again, is the variable beta. We're going to return the zeta to the scaled equations. You might recall that F is generally an order of magnitude larger than zeta. Hence, we have argued in the scaled equations that you could ignore this term, but we're going to return it here as a small term, and one of the reasons to do that is so that we can match this variable on this side with this variable on this side. You should recall at this point that the way we are manipulating and managing these equations, we're always working with the scaled equations. Hence, they are not from first principles representative of the flow. They have been filtered and simplified in some ways to help us with our interpretation. We're now going to divide through by this absolute vorticity, the zeta plus F, and on this side we will leave the horizontal divergence. We're going to assume constant density and temperature, then we're going to use mass continuity to replace the horizontal divergence with the vertical divergence essentially, or dw dz. We're going to integrate with height from z1 to z2 over a layer of depth h. Hence, we're going to have a layer in the atmosphere where there is a depth of h. That is what this equation is showing the integral of both sides with respect to z, going from z1 to z2. We're going to leave this left-hand side as it is for right now. We're going to use the assumptions of our problem to do this integral here of dw dz, and what we get here then is wz2 minus wz1 over the depth of the layer. We're then going to recognize that wz2 minus wz1 is dh dt. That is, how is h changing with time? Because if you imagine this is again really the divergence of the depth of the layer, and hence you can imagine the top and bottom surfaces of that layer stretching or coming together, compressing as time goes on. Hence, we will be able to write the whole equation by combining everything on the left-hand side of d by dt, where we're explicitly stating here we're looking at the horizontal derivatives here. We're looking at the xy plane of zeta plus f over h is equal to 0. This quantity here, the zeta plus f over h, is the potential vorticity. This is the potential vorticity under a set of assumptions that we use to derive the equation, where we use constant density, constant temperature. So this is only relevant to an atmosphere in a shallow layer. If you were to conceive of the atmosphere made up of many shallow layers, you could imagine this equation being applied in each of those layers stacked on top of each other. The key here is that potential vorticity is a measure of absolute vorticity relative to the depth of the vortex. If, as depicted here, here's a shallow and a high layer. So these lines here are the top and the bottom of a layer. And you see here that the depth has changed here, so this has, what we might say, has stretched out. And one of the things that you see has to happen